I want to make sure to introduce Pedro Szekely. Pedro is the director of the Artificial Intelligence Division at the USC Information Sciences Institute, which is a group of more than 150 people with all kinds of backgrounds and interests in artificial intelligence. And he's also a research associate professor in computer science. Go ahead, Pedro.
Well, thanks, Yolanda. Oh, I see we have two speakers. Okay, so our first two speakers are Jon and his cat. They're going to talk about responding to unexpected events. So Jon, please go ahead.
Thanks. I wish I could say that the cat on my shoulders was an unexpected event, but she's there a lot and I've just learned it's best not to fight. I wanted to talk in more generally about when things happen that we don't expect, of course. And a lot of those things that happen are disasters, crises. I'm sure you can think of any number of recent unexpected crises that we've had to respond to. Sometimes we want to respond at a large government level and an international level. But in general, every time there's a crisis, there's something different. It's hard to fight the next new war because that's what makes it a crisis. And you really generally have a lot of time pressure and resource limitations. There's often very high stakes that you really want to make sure that you do a good job responding to. There's also often a lot of information coming in that you have to synthesize and figure out what to do next with. Often, since the problems are new, we need to have creative solutions in order to solve them. And so this is really, I think, fundamentally the job of humans and will continue to be for some time. But we believe that AI can actually help to make humans be better humans. These approaches can help manage a crisis. So some of the things that are important are, for one thing, unifying the kind of information that's coming in. So you want to make sure that there's as little barrier as possible between you appreciating the information and that info. So if it's coming in a language you don't understand, you need to be able to translate it. And you may not know what language you're going to have to translate with much advance. And also if it's coming in, say you have 911 calls, you have to it's probably better to have them all in one easy to see form. There's often so much information that you really only want key elements. So you may only want to know the general topic of, say, an emergency tweet. You want to maybe know that there's a shelter request or a water main broken. Or you may only want to know people and places and facilities and the way they're relating to each other. And then furthermore, again, to be able to come up with creative solutions, we think it's going to be helpful to have maybe some kind of proposed possible solutions that you wouldn't necessarily think of yourself. I think of how, when Google Maps started giving route information, that kind of changed the way I thought about how I was doing my daily commute. And this kind of thing, it didn't necessarily give me the exact solution, but it led me to think about new approaches. So anyway, if we go to the next slide. There's kind of two overall things that we keep in mind here, and I'm going to talk about various aspects of each of them. One is we want to make tools that are going to make humans better humans, maximize efficiency. And so this means that we're going to have people who can accomplish a task now that couldn't accomplish it before, and that are going to allow better data engagement. And then the other thing we want to do is do our best to be prepared. To that end, we're going to use a lot of transfer learning techniques ultimately, where we're learning some kind of generic model that we can then specialize quickly when we learn about our new unknown unknown. So we move on. So the kind of synthesis of a lot of this, and I'm going to break down into a few components, was the work of this DARPA program called Lorelei, which ran over 4 years. In that scenario, we had to do speech recognition and translation and name finding and all these things, but they were for some new language, for some new crisis. And we wanted to deliver systems. We did deliver systems within 24 hours to try to leverage that data. So what that ended up taking the form of is dashboards that would analyze and synthesize all of the data that we had and show, for example, the kinds of needs that were being requested by people, often in the form of tweets or sometimes reported in the news. So things like evacuation need or search and rescue operation, and pinpointed them on maps and put them in English. And so the point of this is to give this information to providers and to first responders so that they can make the correct decisions. And so the hope is to prevent mass casualties. We actually then use these in deployments in some NATO exercises in Macedonia and Montenegro to great effect. Next slide. And so to break down a little bit further, so some of these tools that I mentioned before, I want to highlight two of them. One was a universal Romanizer. So the idea here is leveraging the Unicode table and metadata that's provided in there. We built a fairly simple tool at the end of the day that takes anything that's written in Unicode and attempts to make it roughly pronounceable. Sometimes in a way that's not exactly obvious, but the outputs of these could be used to, for example, find cognates of names, find related words, and try to do to get some appreciation of what's going on. And these were often used, and they are still used in more downstream techniques. And another tool was a translation editor. So the idea here is often we would have almost no information. In this case, I think we were translating Uyghur. We had no speakers of the language and didn't know anything about it ourselves and couldn't build MT systems, but we could at least build a small amount of data that we could use to train or bootstrap or even evaluate. And this tool gives us at least some word hints so that we could try to rephrase things ourselves, and gives us morphological components and possible dictionary matches. And putting this all together, we're able to build data sets pretty quickly in 7-day evaluations. And we adapted this into information extraction and other kinds of annotations with our partners on this big team. And then we also built these kind of ready to go machine translation systems where we would build a large system ahead of time. This is using a technique that's very common now in machine translation. We were pioneering this in 2016. To build a large, say, French to English system. And that just teaches you about translation so that when you then learn what your language actually is, and you have a very small amount of data, you can fine tune your system and do a lot better. And we broadened that to an even faster approach that was even better at adapting, where you would have many different languages translated ahead of time in this kind of universal model and then fine tune it quickly. And plus, these are kind of small things, but they add up to a lot, is picking hyperparameters can be challenging. You don't want to have to build a system, evaluate it, then try again, build another system. So we devised a decent hyperparameter selection specifically on how much you break up a word into its morphological or pseudo-morphological components to get best results. So these are all for being able to develop your systems very quickly. Okay, next slide. All right, so moving on from that, we're looking to do more of the kind of complex task analysis and be able to aid with that kind of thing. And so you can think of an event as a series of small steps, and we want to know the best decisions to make at every point there. And that's a lot like playing a game. And in fact, we are inspired by these automatic video game learning systems that use a form of reinforcement learning called deep Q learning. And we applied this to what are text-based games, which is a very old form of entertainment from before the graphics age. But it's a good model of getting information in and then having to decide what you do next in a fairly open form. And so we could use deep Q learning to learn how to, say, play a series of cooking games. But what we wanted to do is be able to respond to the next situation. So by integrating this deep Q learning approach applied to text games, we incorporated that with these very large language models. A very famous one is BERT, which have tons and tons of English data and allow you to essentially access background knowledge. So by integrating BERT and using annotation learning to be able to train quickly, we were able to learn how to play cooking games, but then we could use that system to then play games we'd never seen before, types of games we'd never seen before, like treasure hunting games. And so the point is we'd like to gamify the crisis response system. And then the last thing I'm going to say is, sometimes you just want to brainstorm and just kind of like talk about stuff and build upon each other's ideas where there's no wrong answers. And for that, we take inspiration from improv comedy, where a founding principle is to yes and, which is to say you accept what has been said and then build on top of that. And so we built a dialogue agent that was a better improviser, that actually contributed usefully and didn't negate what people had said and wasn't boring. And so you can use this actually. If you go to spalin.isi.edu, you can try it out and just chat about whatever you feel like chatting about. I made this small chat about trying to inoculate quickly. Our hope is to be able to use this or models like this to try to figure out more unique solutions to the next difficult problem whenever it comes along, and have another voice in the room. Okay, I think I'm definitely out of time, so thank you very much.
Thanks, John. We'll have the questions after all the presentations are done. So the next speaker is Mayank Kejriwal. Welcome, Mayank. Mayank is a research assistant professor of industrial and systems engineering and research lead in the AI division. So please, Mayank, go ahead.
Right, next slide. So child sex trafficking is a heinous crime that has gotten worse with the advent of the web. According to a white paper that I co-authored at a roundtable in the Concordia Summit that was co-held with the UN General Assembly in 2019, the volume of child pornography has gone up by more than 6,000x in the last 20 years. An unknown but significant portion of online advertisements describing escorts, illicit massage parlors, and other sexual services feature minors and trafficked victims. According to NCMEC, or the National Center for Exploited and Missing Children, 1 in 7 of the 23,500 plus runaways every year in the US are trafficked for sex. At the same time, we decided in that roundtable that AI is uniquely positioned to address this problem through network science and natural language processing. Next slide. As part of my collaboration with a federal agency, we've developed a human-in-the-loop system that ingests millions of raw advertisements selling sexual services. The system attempts to discover minor victims in these ads. Other than the AI algorithms, of which I'll describe the intuition shortly, selective validation is an important step in our workflow. Selective validation is the use of online tools, usually available only to law enforcement and select stakeholders, to verify the precision of the AI's recommended leads by searching for the top leads in real time. Outputs from domain experts guide the post-mortem analysis, which helps us to refine our algorithms. Next slide. So as shown here, the core elements of our algorithm rely on an ensembled information retrieval system that relies on sophisticated signals, many of which are themselves extracted using machine learning. Combining these signals, which include use of certain emoticons, metadata information, and linguistic cues, yields a ranked list of ads with high probability of the victim being underage. Our work on human trafficking has already had tremendous impact in the US and has led to several convictions. Arguably it, along with other related efforts, has put human trafficking on the map, and in the last year alone, several major hotel companies and other organizations have come out with strong statements on recognizing and fighting human trafficking. Next slide. In 5 years, our goal is to create a smarter human-in-the-loop plus system that is more proactive than reactive. For example, potentially phone numbers and other details of missing children, runaways, or teenagers from NCMEC could be used to do a smart lookup in real time, allowing faster rehabilitation of the victims before much damage is done. Next slide. In 10 years, we expect an even more exciting era where the AI and the post-mortem analysis start to inform policy more broadly. These policies will rely on hard science and will lead to broader societal shifts in how trafficking is viewed and tackled. We also hope and expect to see more international cooperation and data sharing and governance on this issue. Thank you.
Thank you, Mayank. We'll have the questions at the end. So we'll go to our next speaker. The next speaker is Jay Pujara. Jay is a research assistant professor of computer science, and since January 1st, the director of the Center on Knowledge Graphs at ISI. So Jay, please go ahead.
Thanks. So I'd like to discuss financial accountability. Next slide. And when we think about financial accountability, one thing we can think about is the American dream. And what we expect in the American dream is that we work hard, we innovate, we create new products, new ideas, and around them we build a business that will ultimately grow and prosper. So this to us is the American dream. Next slide. Unfortunately, this isn't how reality works. Over the last few decades, most entrepreneurs have failed. In fact, if you look at the top graph here, within the first 5 years, only 49% of new businesses survive, so more than half have failed. In the bottom graph, after initially creating many jobs, new businesses every year of their first decade lose jobs in aggregate. So you can see that instead of being net job creators, these new businesses are creating job losses. And so as a result, we view this as the failure of the American dream. It results in decreasing economic growth, reduced innovation, it hurts global leadership, and these types of failures disproportionately impact underrepresented minorities. Next slide. So when we ask, can AIs be one of us? One question we can ask is, can AI work with us to help preserve the American dream? Can it become our partner and help us solve these sorts of problems and succeed and thrive? Next slide. So as an example, I'd like to introduce you to Grace. Grace entered the USC Hack for Hope COVID-19 challenge last year. And what she wanted to do was build an app called Bridge, which would help long-term remote care of elderly. And so in order to build Bridge, Grace needed to know who her customers might be, what technology she needed to either license or develop in order to build her app, the partnerships she could engage in order to be more successful, and finally, her unique competitive advantage relative to the other apps and other services available. Next slide. So right now, Grace has two options. She can use free tools, and those are really poor. You can type in Google's elder care, and you'll get lots of fairly useless links. Or you could use an expensive commercial tool, which has a lot of domain knowledge, but is inaccessible for most new entrepreneurs. And so we term this problem information inequity. And this is the problem we want to address. The way we're going to do that is via an open knowledge network. So this is a knowledge graph about businesses that includes competitors, suppliers, and customers. The way we build the business open knowledge network is to use lots and lots of data, web pages of companies, patents they filed, structured data and spreadsheets, their presence on social media, as well as regulatory filings at the SEC. We take all of these different components and run them through a pipeline of information extraction, ontologization, entity resolution, and deep learning-based embeddings to create this knowledge graph. And using this, we can produce a resource that's open to all, as well as provide these services for business plan analysis, customer discovery, innovation analysis, and supply chain partnerships. Next slide. So one tool that we've built in the last year as a prototype of this is an entrepreneur's portal, where a new entrepreneur can describe an idea or a technology, click a button, next slide, and get an analysis of the competitors, customers, technologies, as well as the relationships with existing work. Next slide. Beyond entrepreneurs, this business knowledge graph is helping us answer many other questions. The Patent and Trademark Office is very interested in how patents change hands over time and how that affects innovation. The SEC is interested how companies' public statements match their regulatory filings, particularly the structured data within them. We've been working in an NSF grant to find supply chain alternatives, so local manufacturers who are manufacturing PPE such as ventilators or masks can find replacements for their suppliers who may have been impacted due to trade or other restrictions during the pandemic. And finally, we're asking how the CARES Act and other COVID responses are helping the small businesses that are really struggling right now. Next slide. So if we succeed, if we can build this AI that is part of the American dream, we estimate that we can create over $1 trillion of GDP growth and over 5 million jobs by reducing business failure rates, eliminating the gender gap, and helping female minority businesses achieve economic parity with their peers. Next slide. And so together, we believe that if AIs can be one of us, we can revolutionize access to business knowledge, improve entrepreneur success rates, help minorities thrive, build an ecosystem that's reusable across many different fields, and improve our financial system to finally advance the American dream. Thanks.
Thank you, Jay. The next speaker is Yolanda. Yolanda, you all know her, research professor of computer science and of spatial sciences, director of major strategic AI and data science initiatives, and director of knowledge technologies, principal scientist at ISI. Yolanda is going to talk about AI scientists.
Thank you, Pedro. I am very excited about the prospects of AI for science. In particular, what I see is that a lot of really cutting edge, deep questions in science require enormous amounts of effort, and they become hero research efforts. So for example, the discovery of pulsars require building a large hadron collider, but once the data was collected, about 4,000 scientists collaborated to discover pulsars. In neuroscience, we collaborate with the Enigma consortium that puts together data from all around the world, dozens of countries around the world, lots of different institutions, and the articles that they publish tend to have several hundred authors. So AI should be able to contribute and help in terms of scientific collaboration, integration of data, integration of knowledge, correspondences of scientific theories and beyond. AI has been a domain for looked at scientific discovery as a domain from its early days with Herb Simon, one of the founders of our field, studying the cognitive aspects of AI, through to a lot of work, early work at Stanford on the importance of scientific knowledge to drive discoveries, and a lot of other work over the years, ranging from machine learning to robotics to constrained reasoning. Indeed, many recent announcements you can see here. I have some examples that look at computational sustainability, environmental aspects of research using constraints, biology using all sorts of knowledge technologies, in addition to machine learning, deep learning. Great news last month on the development of a system that actually can predict protein folding and protein structure pretty well, which is very exciting, and also natural language to extract and synthesize findings from the literature. And in fact, AI is already transforming science, but I think we have further ambitions for AI. One of them is that I believe that scientists can be better. I believe that we can help individual scientists do better. So as humans, we are not necessarily systematic. So the graph at the top shows the difference between a study that was done over 10 years to read the published literature and extract the fossil record. And an automated AI system did the same thing. automatically, being able to refresh its findings and its compilation over time, many times over, and actually found a lot more fossil records than the humans did. This was very surprising to me, but it means that humans are not necessarily systematic or complete. Also, humans make errors. So I cite a paper from a student that tried to replicate a study by Harvard economists, and there were some errors in the way that they looked at the data that impacted the paper. There's also biases. So I show an example here at the bottom right of an AI system that generated all the hypotheses consistent with some paleoscience data. And actually, some of the hypotheses had not been discussed in the papers by the scientists that were looking at that data. And we do have some biases about the theories or the hypotheses that we tend to gravitate towards rather than being objective about all of them. And then finally, in our own work, we find that we are not very good at writing scientific papers as humans. And so we want to be able to improve the way that science is reported so that we can build on each other's work. So some examples of the kind of work that we do, one is automating machine learning. This is an example from looking at time series analysis. So we work with scientists to understand what are the general analysis strategy that they use, the different steps, different approaches to each of the steps, different methods, what are the constraints to each of those methods, and represent all of that knowledge as a multi-step template that we can reason over. We include a lot of data and algorithmic constraints and a lot of abstractions on the different steps that we can then automatically instantiate. And what we find is that these templates are valid methods, and so people trust them, and they help us do a systematic search over solutions, over possible analytic solutions. So, so it can lead to better solutions than a human would without all of this expertise and background knowledge. Another example of our work is on automating hypothesis-driven discovery. So we find that when scientists ask a question, they'll go through a meta process of asking, well, what kind of data is available for this question? Maybe my colleagues have collected this data before, or maybe I'll collect it myself. And once I gather the data, depending on what data is available and its quality, etc., I decide on what methods to use. And then finally, if I have evidence from different types of data, I'll reflect on the findings and decide if the hypothesis is supported. So this kind of meta reasoning about science is very important, and we're using it for genomics, also for neuroscience, for other kinds of omics analysis. And what we find is that by having this systematic exploration of all the possible algorithms and data sets, reference data sets and sources in biology, we can expose inconsistent results and potential problems in the findings of individual papers. Another line of work that we are doing is looking at environmental sciences. So looking at natural and human processes, how does water availability and water use affect food shortages and future drought response. So we have models of natural and human processes. Some of them are hydrology models with deep physics, others are machine learning, empirical based for economics. Some of them are hybrid, some of them are agriculture models that have a lot of biological knowledge. And we represent a lot of metadata and constraints about what the models are, what their assumptions are, what kind of data they require, what assumptions they make, etc. And so what we find is that we're able to reduce the modeling time and create integrated models more quickly. Usually integrating 2 or 3 of these models can take 2 or 3 years, even if it's a little bit complex. So we can do this faster, but also we can expand the choices of possible interventions that the models are able to analyze and do what-if explorations. Finally, I also wanted to mention work that we've done to facilitate scientific data integration through AI and through semantic crowdsourcing of vocabularies. So this is work in collaboration with paleoclimate scientists. If you know the hockey stick diagrams, they create these, and it takes them also several years to do because the data is so diverse. Some of them look at ice cores that contain air bubbles of different characteristics, and others will drill in the ocean to see what kind of coral was growing hundreds and thousands of years ago. So they have very, very different data. And what we did is help them converge to a shared vocabulary within the confines of working online and while they were describing their own data. So this is very exciting that we were able to mediate this collaboration to produce scientific standards. We have a lot of projects, I mentioned a few, to capture scientific knowledge and reasoning. And overall, I think that if we capture scientific knowledge and we enhance capabilities of AI to collaborate with humans, to be reliable, to understand the context of what they're doing, to take initiative to learn more things, then I pose the question of, and the challenge of, will AI be able to write the scientific papers of the future? And I believe that little by little, AI will be able to do the more routine analysis and the more routine work in science. And there's a lot of possibilities. I think in the next 2 decades, we will see enhanced capabilities in terms of AI assistance for science and AI scientists that will be able to reproduce articles, design their own experiments, and eventually become co-authors. And some of my colleagues even want to pursue a challenge of AI to win the Nobel Prize eventually. Thank you.
Thanks, Yolanda. Okay, our final speaker is Marjorie Freedman. She's a supervising computer scientist and a research team leader at ISI. And she's going to talk about trust and security. So Marjorie, please go ahead.
Thanks. So I'm going to talk about the intersection of trust and security and most of what I do, which is looking at natural language understanding and how we can use natural language processing and AI techniques to understand what people are doing and help people. And that intersection for me is trying to detect and respond to social engineering attacks. But before I dive into talking to you about that application, I just want to give a shout out to a lot of other really critical applications in the space of trust and security that are places where AI is helping. And so I just want to kind of overwhelm you with all of these examples. And so Yolanda, next slide. So social engineering attacks are, I think, something that most of us have experienced or are at least aware of. Keeping information secure is hard, in part because we as people are weak links. We share information when we communicate. Many of us need to communicate with people we don't know. And when we're in a hurry, we don't verify that we're communicating digitally with the person that we think we are, and we share critical privileged information. Spear phishing attacks can be very targeted, and a number of us were targets about 18 months ago with the gift card scam that went around, where the attacker had identified department chairs or directors and targeted those who worked with that person, spoofing that individual, asking for gift cards. And this risk provides an opportunity for AI to help. AI can help detect and prevent the attacks. In doing so, it raises the cost of the attacks. And so just making them harder can reduce their numbers. And we can even help identify attackers. This is a challenging area. The attacks are evolving. It's a bit of an arms race. The data that we want to look at here is private. So we're not interested in just Newswire or blogs or information that's been published to the world, but instead we need access to email. We need access to things beyond email, because these attacks are coming in through SMS, through social media platforms. So, next slide. I'm going to give you a quick overview of how we do some of the detection. What we found is most effective is trying to take advantage of the fact that senders are saying they exist in the real world, and so they should. And just like we are present in the real world, we should be able to find them in the real world. And so to describe this process of vetting, I'm going to walk you through an example talking about both how I vetted what I think was an attack and what it involves to bring together AI pieces to build this vetting system. And so I got this LinkedIn request from somebody that I didn't know. And I noticed that actually they had already connected to one of my colleagues. I looked at it and I thought, I didn't see an announcement of a new writer at ISI. I'm surprised. And so already I was doing relation extraction. I was identifying Information Sciences Institute as an employer. I was noticing the job title. I was using my background knowledge of what was happening connected to me. And I thought, okay, I'm going to go to our directory and look them up. And so I resolved Information Sciences Institute to isi.edu and found our directory and looked for this person, and they weren't there. And then I reached out to my colleague and said, do you know them? And the answer was no, they did not. And we both decided this was probably an attack. So what we're trying to do is a combination of being able to automatically extract those features and then reason about the features. And that's online vetting. That's how we try to place people in the world. We're also looking at communication internal signals and trying to identify anomalies. And so this can be a mismatch between the metadata and the body of an email. This can be a mismatch between a particular message and the history of communication with that sender. So using authorship detection techniques. And this can be a mismatch between the content of the message and the topics that the recipient usually talks about. And so any of us getting a request for gift cards is probably a surprise. These set of message internal features are all weak signals. They're all cases where they don't mean an attack. And so one of the things we have to balance here is being able to detect these features and then reason about them and decide when there's sufficient risk that we want to decide this is an attack, put something in quarantine and possibly annoy the end user who has to go find it. Next slide. So we're also, in doing this, making the attack more costly. Requiring an online presence means that sending an attack isn't just sending an SMS or an email, but you need a website, you need a phone number. These are things that we can verify. We're exploring using dialogue bots to engage with the attacker. Responding takes time and it isn't a mass mailing. And responding opens up the potential that we can identify the attacker. Next slide. And so I'm going to wrap up with, this is a person example, not a bot example, that I think touches on the theme of this symposium. I pulled this originally because this looks like an aspirational aspect of a dialogue bot for me. This victim, V, looks pretty good. It's responsive, it's asking reasonable questions, it keeps the attacker engaged. But then if you look more closely, the bot A, uses the same exact language twice. So probably the attackers are actually already using these bots and tricked my friend who responded into spending a fair amount of time responding to this attack. So that's the end for me.
Thanks, Marjorie. Thanks to all the speakers. So we have time for questions. So please post your questions in the QA. We have a couple questions that were already answered, but we can start with them. I thought they were very interesting. So there's a question for Jay on solve the important problem of automatic ontologization. which he alluded to when talking about building the knowledge graph. So Jay, can you sort of talk a little bit about how you do this?
Sure, I think it's a great question, and it shows how we all work together on this problem. So I mentioned a couple of other talks that have occurred earlier in this AI symposium. One was by Craig Knobloch on threading data, and the other earlier today was by Pedro on all the world's knowledge. And so in both of those talks, tools such as Karma, T2WML were introduced for automatic ontologization of data, either in the setting where an automated prediction is provided for the ontology, or one where a human can look at those predictions and decide whether to correct them or accept them as they are. And so I think those are great tools that we've developed. And one of the really interesting problems that we're working on is to use all of the context that we have. So, as I said, we're using web pages and text. And for that, it's not always structured data, but we're looking at how these vector embeddings can be turned into structured data with these automated ontological mappings so that you can get a knowledge graph from both the structured and unstructured data that's available.
Okay. There was a question for Mayank, and Mayank actually had to go because he had an important call related to his work on human trafficking, and so he had to go do this. So he's not here to answer. I know from his work that he's been working with human trafficking data for many countries. And he has found that the patterns of trafficking and how ads are posted and so on are actually different in the different countries. And he has done some work to address this. So I encourage Carlos to reach out to Mayank, and he'll be able to tell you more about how he handles this problem. There's also a question for Yolanda that is asking her about the examples of using AI in the semantic web domain.
Examples. So we see increasingly scientists desperately trying to integrate data and other information. And so in biology, semantic web technologies are really pervasive and have enabled a level of communication across disciplines that is really remarkable. Biologists had to become ontologists and started practically with the gene ontology, and that trend continues to these days. We see similar trends in geosciences where people want to describe physical variables in a according to some standards or adhere to some conventions, and that's growing increasingly. And I think we see this also in material science with the desire to describe different materials, different compositions, different properties. So the semantic web is certainly a big ingredient of the scientific enterprise, and I think an enabler of AI technologies.
Okay, thanks, Yolanda. There's also a question for Jay about, why did you call your project financial accountability?
Yeah, and I very briefly answered that to say that there are actually a lot of financial accountability applications that I feel are less relatable. You're not an SEC regulator, Henry, who has to look at these and try to figure out what type of financial malfeasance are. So I did highlight some of these applications that are from the BOKN that we're developing. But I think this entrepreneurship is a really visceral example that we can all relate to because either it's something that we maybe aspire to or someone we know has actually done where they've tried to start a business or are working to create something new and need that support. And if AIs could be part of that, I think it would be a really inspiring future for us.
Okay. So, I have a question for Marjorie. So, you know, as we develop these technologies to detect that, you know, we're being victims of people trying to get into our organization, and how do we build systems that somehow learn to improve themselves as the attackers, you know, learn to deal with the sort of defenses that we erect, you know, to protect ourselves?
Yeah, I mean, I think that's a really good question, and I think it's really hard. I think we're hoping that some of the approaches that we're developing that are anomaly-based, that just identify the unexpected, can provide warning, even if they're less certain. So you end up with an unknown person contacts you, and what they're talking to you about is either very risky, and so that's another factor, and I think how you want to approach this. And but if you abstract away from the very specific scam to something like gift cards to this looks like a message that isn't typical for Marjorie, then what you need is a model that's constantly updating its information about Marjorie, but not constantly updating its information about the scam.
Yeah, okay. I mean, it's very interesting. Now during the pandemic, I get lots of text messages that tell me that my Amazon package is delayed, and I should click here to see when it's going to arrive. And you know,
yes, I get lots about my car warranty, and my car is no longer under warranty. So I mean, I think that there will continue. I also think that there are some things that are really preying on your sense of urgency, and occasionally everyone forgets to do what they're supposed to do. And in, you know, having simple approaches that remind you not to do that. So Amazon doesn't send you SMS with a link is probably the way to go.
Okay, so I had a question for Jon, as you know, the work on the low resource languages is also quite interesting for knowledge graphs, because you know, Wikidata has very sparse information in these languages, and you know, they maybe the community has a harder time using these knowledge graphs, but because they have very few labels in their own languages, and so wondering whether there's a way to also enhance the multilinguality of you know, knowledge graphs like Wikidata with the work that you have done in Lorelei.
Potentially, I would say. So I must admit, I'm less immersed in the forms that Wikidata takes, and so my naive thought is that it's, you know, largely isolated terms or very short phrases, which, you know, I think for really kind of understanding language transfer, you really want to have context. Otherwise, you're just kind of doing a simple relabeling, which is not really translation. So in terms of building the knowledge graphs from text automatically, definitely, I think you know, you could use the translation approach, or you could just use the more and more there's multilingual representations that are able to leverage various other kinds of transfer learning and meta learning and multitask kinds of learning, so that you're going to learn the knowledge about how to build the graph from the labeled data that you've got from English, and be able to apply that to the new languages. And I think that's really important, because you don't simply want to translate English Wikidata into Gujarati, I mean, that doesn't give you any more information, really, except for maybe some extra terms, which you have to begin with. Otherwise, you wouldn't be doing that. You may as well just make a term list. What you really want is the novel information that you're not finding from English sources. And so to that end, you really want to use that kind of transfer so that the task of forming the graph is done in a native new language way, which you again can get from transfer of the task in multilingual models like MBERT and various other newer trillion parameter kinds of models.
Yeah, I think there's an opportunity for leveraging, you know, the Wikipedias in some of these languages where they describe, you know, concepts and items that are very culturally dependent, for which we have very sparse, you know, pages in the major languages.
Right. Yeah, you're going to get a different length article about the same thing depending on where the culture is with their interest in that thing.
Yeah, absolutely. So we have time for a few more questions. If we, you know, I don't know if anybody in the audience has other questions that they want to ask our speakers today. Or questions that the speakers want to ask the other speakers.
I would like to ask Marjorie, that was really interesting, and Mayank is not here, but I often wonder if we need to have special consideration to children and AI. It's a theme that I know the UN has given a priority to, and UNICEF, but I wonder if you see that in terms of, you know, the security aspects of this, if there's some special techniques, provisions, or special requirements for children that you know, AI could help provide.
So I mean, I think with what I think when judges, so I can't answer for Mayank. I think when judges risk in terms of communication with children differently. And so I think we already, you know, we have non-AI parental controls that whether those be on phones or on what children are able to search for. And I think right now those are typically fairly blunt. You know, there's avoid these websites, and there are cases where important information is actually censored because, you know, of certain terms. And so I think making that type of access smarter is probably an opportunity for AI. And I think if, you know, that when I talked about how we decide when we have a weak signal, is this, what do we do with that information? I think the risk to a child in responding to an SMS from somebody they don't know is higher. And so that notion of how we trust people we don't know, and we trust people that are, we haven't verified who they are, is something that AI would need to address differently for children, because risk is different there.
So I have a question for Yolanda on this of AI that writes papers. So one thing that appears doable is to have, you know, we write the paper and then the AI writes the related work section. And in a way that we never get dinged by reviewers for not having cited the most important works and put, helps us put the work in context, very well, because the AI, in a sense, can read every paper. So is this something you think could, are people working on this, or?
Yeah, so that is probably the hardest part to write about a paper, because you make a lot of subjective decisions about, of a whole line of work, what papers you prefer to cite, or which ones are speaking more to the aspects or the nuances of your work. So that's probably a really hard section to write for an AI system. At least thinking of the next 5 or 8 years. But I do know that I do believe that it's very feasible for an AI system to write the methods section and really describe accurately what work was done to analyze the data. And so even focusing on the method section, we realized that a lot of assumptions, a lot of the steps just don't appear when a human describes how they analyze data. And so there's a lot of impetus from journal editors, but also from scientists to learn to write those method sections better. And you see this, for example, in AI, a movement towards reproducibility in NeurIPS, in AAAI, in the call for papers, in guidelines for authors. And so I think that thinking carefully about what we need to report so that others understand what we did is a step towards having AIs really try to imitate that and report similarly. So I think the method section might be our first priority. I think we can also help design the questions in a paper, right? So to assess, well, no one's asking this question, but look, we have all the data that's needed and we could start the process. So scientists sometimes cherry pick the topics that they work on because they only have so much time in the day, but maybe with AI, we can pursue questions that no one is prioritizing.
So if I may be provocative, if we're going to use AI to write the methods section, we're also going to use AI to distill the information in written papers. Wouldn't it be easier to just kind of avoid natural language altogether? I mean, and maybe. I do wonder sometimes if papers need to be written.
Maybe so. But however, natural language has many great properties, as you know very well. So it's very concise. Sometimes it's ambiguous, which works to our advantage when we have not answered all the aspects of the question. So I don't think we're anywhere near to part with natural language, but we need to use more than just language and start to use more formal structures to describe science, and that will make it more understandable and accessible to AI.
Okay, I mean, we have a few minutes. We got several questions, on the chat. Maybe we go to Terry's question about using AI to help with bullying. Anybody wants to take on that question?
So I know I pointed to a general audience article. I know there's really active work. I don't know if any of us are working on it, but I know detecting bullying, intervening is actively of interest, both in applications. So to try to make applications a happier place for all of us, and also as research.
Okay, maybe one final question or comment from Henry. Maybe AI could blunt the reproducibility crisis by doing some of the work to reproduce an author's experiment or analysis.
Yes, I think the more that we bring AI to science, the more reproducibility will be addressed, because today we have AI systems reading papers and really pointing out that there's not enough detail to disambiguate or to understand or to reproduce. And so AI will keep us honest and ensure that the papers are written with the level of detail that they deserve to be written. And I think if we have AI write papers, maybe we're delegating that rigorous description of the science to professional AI tools that understand how to convey structured information about our scientific methods. So I'm very hopeful that AI is a key piece in terms of the reproducibility crisis. Yes.
Yeah, I mean, I think Jon made an interesting comment, and I wonder whether that future means that, you know, we have papers written for the AIs and papers written for the people, and they emphasize different aspects because, you know, people are good at certain things, and, you know, the AI can sort of make sure that, you know, the thing is reproducible and so on, you know, and I don't need to be convinced about it because I have my assistant that actually, or, you know, this has already been verified. I just need to be told what are kind of the intuitions and the sort of clever ideas.
Yes, however, there's many different kinds of people and many different kinds of AI. So in some sense, your papers could be customized to the audience, right? So a reader that is really trying to see what software tool you use, how did you calibrate the parameters, how did you decide how to use the data, you know, that's a lot more detailed than the casual reader that just wants to get a gist of the findings. So, and possibly the same thing with AI systems, the AI systems that just want the main conclusions and some provenance information versus an AI system that really wants to rerun the entire method. So I think there's a lot of audiences talk about, you know, designing for inclusion and for diversity. There's a very diverse set of audience for scientific papers, I believe.
To some degree, I think there's a move towards that. Now, I mean, you can, instead of having a block of text that lists what all the hyperparameters are, I mean, we still have that, but we might not need it because you could just have your GitHub link that has a parameters file. So if you want to do reproducibility, there's the one button. If you actually want to know what the hyperparameters are, there's a config file. Now, if you want to know why the hyperparameters were chosen, that should still stay in the paper.
Yeah, the method of that choice, yeah.
Okay, Yolanda, we run out of time. I just want to mention, you know, Henry Lieberman posted a link to his own work on bullying, for which, you know, Henry is actually very well known. So thanks, Henry. And, you know, Yolanda, any final thoughts you want to make about the session before we close it?
Yeah, I think just to say that I think it's very important, this notion of AI to take on critical tasks, which is the theme of the session, to really think that it's more than you know, personalized assistance to complete our search or to help us with you know, mundane tasks, but there's a lot of promise for AI to help the world with all these very critical areas. So, but thank you, Pedro, and thank you to all the speakers. This was a great session. I just want to say that we will reconvene at 30 minutes past the hour, 1:30 Pacific. We have a wonderful panel on this notion of critical tasks and critical applications of AI. And then we will close the symposium with closing remarks from Maya Matarik, who's our USC Vice Provost for Research and well-known professor in AI, and by Craig Knobloch, the Director of ISI. So I look forward to seeing you all in that closing section. We'll reconvene then. Thank you. Thank you, Pedro.
Thanks, Yolanda.